Hello and welcome to YMT211 Discrete Mathematics. Today we are going to discuss the first part of Chapter 2, and I would like to highlight the fact that I delayed discrete mathematics topics since I'm teaching you the similar courses, programming languages and logic circuits at the same time. So the idea is like this. I exactly postponed the discussion of principles of logic or the fundamentals of logic in discrete mathematics until we cover the basic chapters of the aforementioned courses, and for that reason it would be much easier for us to go deeper in discrete mathematics and discuss the logic topics. Why are we discussing logic topics in discrete mathematics anyway? In a very basic sense, logic itself actually touches a lot of parts of our implementation in machinery realization, or in our computation process in brief. We explained about this in programming languages. We explained about this in logic circuits, so that's why I don't have to go through all that introduction that we have already provided. But for those who maybe have forgotten, let me just refresh your mind by a few points. At the machine level, what do we have? We have usually some symbolic representation of series of ones and zeros, and we need certain instructions for them. And in that case, it's much easier for us to deal with the machine based on series of ones and zeros with a simplified sort of a language or simplified processes. That is where the logic comes. Logic is exactly, instead of the way we deal with human instructions, we speak to each other and we give instructions. For example, like now I tell you, listen to me. The computer wouldn't understand this exactly, but if we simplify it and represent it by a symbolic representation, then it would be easier for us to translate it to series of ones and zeros and then apply it to the hardware, to the machine lower level or the low level language that we have in our machinery. That's exactly the idea. And it's applied a lot in discrete mathematics, and we have a relatively long chapter, and that's why I divided it into three parts. Let's just go through the process one by one and see how things will go. Basically, the essential part of any logic components in discrete mathematics is the statement or the proposition, or sometimes we refer to it by assertion. Assertion is what? Is a statement that can be evaluated to true or false. Either true or false. It depends on the outcome of its own evaluation. But now we are not addressing what's the outcome. But all we can say, it can be true or it can be false. So there is a possibility, it's an assertion. Alright, let's just take an example. One of the common examples in Turkey, it's like you can say a stereotype maybe, or a misconception about the capital city of Turkey. A lot of people think that Istanbul is the capital city of Turkey, which is not true. Ankara is. But this is an assertion, and it can be evaluated to true or false. And usually in discrete mathematics, what do? We do like this. Instead of dealing with the whole sentence like this, or a statement or an assertion, we refer to this by a statement. We replace it by a lowercase alphabet. So instead of dealing with all this assertion, we say it is represented by maybe P or Q or R. It doesn't matter. So logic is an important area in discrete mathematics. Also is an assertion. Why? Because this statement or this assertion or proposition may be true or false. Alright, let's take another example. It could be a mathematical equation. It's possible, and that's exactly what we do when we have a logical representation of a mathematical equation. 4 times 3 equals to 12. This is a mathematical equation with an outcome. It could be true or false. Maybe I can put it here equals 11, which is false. Here is true. And as I said, at the moment, now we are not particularly careful about the outcome, true or false, but we just explain the idea of the assertions or propositions. Let's move a bit. For primitive statements, primitive statements are actually composed of just one part of assertion or one part of preposition. Means what? We do not combine other types of assertions along with it. Now look at this. This Istanbul is the capital city of Turkey is an assertion, which is a preposition that doesn't have any combination with it. We cannot simplify it any further. How can we? We cannot. If we say Istanbul is the capital of what? City of Turkey is what? So we can't simplify it in this case. Again, if we say 4 times 3, then what? You can't build a preposition or an assertion unless you say equals to something, and in that case you can build your preposition, and in this essentially this is a primitive statement in this case. It's not combined. All right. We have other types of statements that cannot be evaluated to true or false. Now think about, not all statements that we have are assertions. What a beautiful day is not an assertion, it's an exclamation. You're just surprised or puzzled, or maybe you want to give an instruction. Instruction in this case is not an assertion. Clean the whiteboard, for example. Listen to me. Also, this is not an assertion. It can be translated in computer language, but this is not the type of assertion we are speaking about. All right, let's move a bit. How can we create other statements from primitive statements? We can negate them. The first to learn here is negation. Negation is exactly applying an operation, we call it not. And in our language, or the language that we speak, we use it a lot. For example, if I say Istanbul is the capital city of Turkey and I want to negate this statement, so I refer to this statement by P. So not P equals to this statement. Istanbul is not the capital city of Turkey. We don't say not Istanbul. It's not exactly said this way. But we just need to rearrange our idea. In this case, we negate the preposition represented by P and represent the logical form of it. Linguistically should be correct and understandable. So Istanbul is not the capital city of Turkey, and that's how we do. Why I'm saying this? After a few parts, we will have some type of questions that ask you to represent symbolic equations or representations or logic expressions in sentences, English sentences. All right. So how can we combine sentences? We can use logical connectives. What are these logical connectives? We had a simple idea about them in logic circuits, but now we will take them in details. Negation is applied to only one sentence, and you already know it. We explained about it in logic circuits, but for those who do not know it, it negates the assertion or the preposition. We have something we call conjunction and operation. We explain about it in a while. It's like this hat. Okay, for the disjunction it's V or, right? And then we have the exclusive or, X or. We explain about them and their truth tables very soon. We have the conditional or implication. I usually refer to it by implication or the conditional statement. If then we have the biconditional, this double-sided arrow. We have the arrow for the if then. We may represent it by if and only if. This is the way we represent them or say them. All right, let's take some examples. Now, as I said, the initial idea is to represent what? To represent, let me take the pen, any assertion by a symbol or an alphabetical, a lowercase letter. So let's say I'm just saying an assertion or giving an assertion. It is Friday. Oh, it may be not. Okay, and then it is raining. Let's try to create or combine these statements by the operators we learn, the connectives that we learn now. Construct the prepositions P and Q, P or Q, P, X or Q, P implies Q. why I'm reading them now, so you know how they are read. And then P implies Q and Q implies P at the same time. Or if P, then Q, and if Q, then P. Okay? Or F, P if and only if Q. So this is the way we usually say them. Let's represent the idea. P and Q, it's easy. It's Friday and it is raining. Okay? P or Q is also easy. It is Friday or it is raining. This is a new statement which is combined. Also, this one is another new statement or assertion which is combined. Why combined? Look at the operator here. Or look at this one and. So we have two statements basically which are actually or which can be decomposed to P and Q. Alright, let's not extend here, move forward. P, X, or Q. It's a bit tricky. It's Friday and / or at the same time. And we use it in English also. It is raining. P implies Q if the first statement, then the second statement. If it is Friday, then it is raining. So if the first assertion, then the second assertion. Alright, take the last. So it is Friday. This is a bit difficult because it is if and only if. It is Friday if and only if it is raining. We have an implication, but double-sided implication. It is Friday if and only if, double-sided. If you understood these statements, you will not have, or the connections, or the connectors here, what we have as connectives. If you understand the representation here, it's extremely easy for you later on to just represent them with no problem. I mean, whatever the statement that I provide you, it would be easy for you to decompose it and represent it in symbolic way like this, P and Q, maybe other R or whatever, or represent it by statements like this, English statements or sentences, and we will take this one in tutorial. Also, please do not worry about the tutorial. I'll give it on time and there will be no problem at all. I just waited to settle the first few chapters of these courses that I mentioned to you, and then we can a bit go faster. All right, truth tables. What are these truth tables? Truth tables, actually tables that represent the truth values of the statements based on certain relationships, and sometimes only the statements on their own. If I give an assertion, what possibilities do I have? Now think about it. Istanbul is the capital city of Turkey. So Istanbul, if Istanbul is the capital city of Turkey, then it is true. If it is not, then false. Then we have two possibilities for any assertion. But if you combine, then we will have different. Why? If we say we have two statements or two assertions, then we have four possibilities. How do I know? 2 to power 2, we studied this in logic circuits, but 2 to power 2 is 4, then we have 4 combinations. And based on these 4 combinations, means the first one is 0, the second one is 0, the first one is 0, the second one is 1, the first one is 1, the second one is 0, the first one is 1, the second one is 1. So we have 4 possibilities, and that's what we do in logic tables. Now for the negation, negation is applied, not statement, or sorry, not operation, is applied only for one assertion. In that case, we just have either true or false based on this assertion. I said for an assertion, we have either true or false. If we negate it, we will also end up having either true or false for the same assertion. But the idea is like this. If the assertion is displayed like this, now we usually start the truth table like 0, 1 or false, true. If you want to start true or false, it's up to you. It's possible, but I usually start by 0, 1. So this one is represented by 0 and this is by 1. We explain about this in logic, or this is false and this is true. So if the assertion P initially is false, if we negate it, it would be true. So not P will be true. So not P will be true in this case. We have, if it is true, it will be false. It's exactly the opposite or the negation of the original statement. All right, let's move next to the truth table of AND. AND is very particular. We explained about it in logic circuits, but if you have forgotten, no problem. Now I'll just brush up your memory a little bit and remind you with it. Now, for AND, there is only one case it will be true, and we must have at least two statements, and operator needs two operands. Operands means what? You would say P and what? So here, and what? So in this case, P and Q. All right, so I can apply it with two operands minimum. I can apply further, it's possible. But for the time being, that's adequate, two operands for this operator. Only one case, if both of them are true, then the outcome will be true. Otherwise, it is false no matter what. So if both of them are false, the first one is false, the second one is false, it doesn't matter. Always false except when the both operands, or all operands if we are applying to many or more than two, are true. This is the condition. So AND is evaluated like this. It is always the outcome P and Q is always false, except in only one case, if and only if both of them are true. All right, let's go to OR. OR is exact opposite, but not particularly. However, it is always true, except in the case when both of them are false. While also AND, when both of them are false, is false. That's why I said not exactly opposite, because we will study the opposite of AND, NAND, later on, or the negation of AND. Now, when both statements are false, the outcome of OR statement, or here the connective, is false. Again, for OR, we must have at least two operands, or two assertions, two statements at least. We can apply to more than that. If we have R or whatever, you can apply, okay? But now the idea here we are speaking about is, if we have two, this is the elementary or the most basic part. If we have two assertions and we want to apply OR for them as an operator, P or Q, what happens? Now, as I said, for the truth table, oh, I forgot, let me just get back to AND. How do we start truth table? In order for us to cover all possibilities, what do I mean by possibilities? Now we have two operands, right? And here these operands are assertions, and we have an operator to be applied to them. These two, in order for us to get the possibilities, we say 2 to power 2. Why two operands? And we have two possibilities, true and false. Okay, so 2 to 2, that's equal to 4, right? And in that case, how many possibilities here? We will have 4 possibilities. How do we list them all? It's the easiest way. Start by 0, 0 or false, false, 1, 1 for the first assertion. For the second assertion, 0, 1 or false, true, then 0, 1. Now look, false and false, false and true, true and false, true and true. All possibilities are covered. And now, if we have more than 2, and I'll explain it after a while, we will go not 2, we will go 4. So it will be false, 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 then true, 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 true. The second one will be false, false, true, true, false, false, true, true. Then we will have the last one, false, true, false, true, false, true, until the end. How do I know that I do this? Again, if we have 2 to 3, we have 3, and in that case we will have 8 possibilities. And in this case, 8 possibilities, we have 4 falses at the beginning, then 4 trues, then 2 falses, 2 trues, so on, then 1 false, 1 true, 1 false, 1 true. We will cover all possibilities. All right, let's get back to OR. So again, for OR, false, false, true, true, false, true, false, true. We covered all possibilities. Then we can find the outcomes. The outcomes always true unless all operands are false, or in this case only 2 operands. Let's go ahead for XOR. XOR is very particular, and we will study its implementation logic circuit within this week. What does it mean, XOR? XOR actually compares the operands. Compares means what? It senses their similarity. If they are similar, it gives false. If they are different, it gives true. What does it mean? Now, P XOR Q means if both of them are false or both of them are true, then the outcome is false. Otherwise, no matter what, P or Q is false and the other one is true, like here, false true or true false, then the outcome is true. We studied this in in logic circuits. However, now we are revising it in discrete mathematics as a part of the syllabus. All right. So again, in the case of similarity, if they are same, the outcome is 0 or false. In the case of dissimilarity, the outcome is true. So either they are both true or both false, then the outcome is false. All right. The same truth table, we don't change anything. False, false, true, true, false, true, false, true. Then we evaluate the outcome. All right. The implication. P implies Q, again, false, false, true, true, false, true, false, true. This is the arrangement of truth table. We will use the bitwise, not now, after a while. I'll explain to you about it. And we use it widely, not in discrete mathematics, rather in logic circuits. However, I'll explain to you as well within this part of the chapter. Now for the implication, we have only one time it will be false or evaluated false when the implied statement is false. Otherwise, if false is implying false, it's true. If false is implying true, then it is true. If true is implying true, then it is true. Otherwise, if true is implying false, then it is false. This is the only case for the implication. It would be implied, it would be evaluated as false. All right, so when false is implying false, that's true. When false is implying true, it's true. When true is implying true, it's true. Only one case, when true is implying false. And now I usually receive this kind of feedback or question from my students. How is it possible if false is implying false, then the outcome is true? Well, this is the way it's evaluated. It's designed. It may not fit your mind. Okay? It may not just fit the logic in your mind, but it fits the logic of the logic circuits and discrete mathematics, and you need to understand it this way. I mean, you don't have to worry about sometimes how is it possible a false is implying false, the outcome is true, or false is implying true, how come the outcome is true? Well, you don't have to worry about that. The rule says like this, so in that case we need to follow it. For the double-sided implication, or if only if and only if, in that case we have P if and only if Q. It's double-sided. Let's get back to this one. Double-sided means, now look at this. False implies false is fine. False implies false, also true. It holds. But true implies false back way here. That creates false. So let me show you here. So what I was telling, here we say P implies Q, okay? And at the same time, Q implies P. All right, so this is what it means. These two statements must hold in order for us to represent the double-sided implication, okay? All right, or the by implication. False implies false is fine. True implies true, fine, because it's double-sided. True, true, false, false. No matter which direction you're following, P and Q or Q and P, so P implies Q or Q implies P, here applies, holds. But in this case, both of them are false. Why? False implies true, we said earlier. It was false here, we said earlier. Sorry, true implies false, we said false, but here we said true implies false again, backside here. That is false. So here true implies false, we said earlier. P implies Q, we said it's false. Now in this case, also true implies false, that's also false. Why double-sided? It has to hold from both sides. From this side, Q to P, and from this side, from P to Q. All right. And that's why only this part, false implies true, is fine, but true implies false is not, and it gets us back to false. So we have true when both of them are false, and true when both of them are true. Now let me show you only one thing, or a simple thing. that you may make a sense of it. Now look at this. Let me get back to XOR. False when both of them are false, or both of them are true, and true otherwise. Now look at this. False when they are, true when they are false, or they are true. It's exactly the opposite. It works as the opposite of XOR. And we will explain about this in discrete mathematics terminology very soon. Alright. Now, as I said earlier, what we need to do in order for us to have like combined statements or negated statements, we need to include them in our truth table in order for us to make the correct outcome of the representation. So let's say if I want to evaluate the assertions P and let's say and Q, sorry, here is or, P or Q or not P or not Q. In order for me to do that, it's easier for us at the beginning as beginners to do what? To create a new field or a new column and negate P, also another column and negate Q. Now look at P. We have two assertions, that means 2 to power 2, 4 possibilities, F, true, true, F, true, F, true. That's fine, like what we did earlier. Negate P, F would be true, F would be true, the negation of F, the negation of 0 is 1, or the negation of F is true, all right? The negation of true is false, the negation of true is false, TF, TF. All right, apply the same to Q. False would be true, true would be false, false would be true, true would be false. All right, now apply OR. So here we are ORing the negations of the two statements, not P or not Q. All right, so we are applying here. True or true is true, true or false is true, false or true is true, only false or false is false. All right, now why are we doing this? I'll come to it in a short while. Just hold your patience. Now, we explained about the negation. Let's just take another way of negation and see, and I have a point to do these things. Again, P and Q. Here we have P and Q, we know it, only true when both of them are true. Now let's negate the whole, this one as a whole. It's a combined statement, let's negate it. So what are we going to have? False would be true, false would be true, false would be true, and true would be false. Now compare it to this. Not P or not Q. I'll carry it to the side, not P or not Q. We just evaluated it. All true except the last one is false. Now look at this. All true except the last one is false. What do you think? They are equivalent. We don't say they are equal. Why? Now this is extremely particular. And if you are asked like a question in an interview, do not say they are equal. The best way to describe this kind of representation is they have the equivalent result, and we have a terminology for it. Very soon I'll explain it to you. But why cannot I, or why shouldn't I say they are equal? Why? The representation of P and Q, the negation of, open the parentheses, P and Q, is not equivalent when we transfer it, when we translate this process in machine language to this process, not P or not Q. Why? Now we have not, two nots here, two operations for nots, and one OR. So we have one operation, 2, 3. Here we have one operation, P and Q, then we have a negation, two operations. So whether we like it or not, they are not equal. They produce equal results. That means they are equivalent, and we have a name for it, a terminology for it. I'll just say it in short while. Then before that, we have conditional statements. Now, if P implies Q, its converse is P, Q implies P. This is the converse. It's pronounced, or it's said, it's spelled, it's referred to by converse, not inverse, converse. So Q implies P is the converse, remember it. Contrapositive not Q, sorry, implies not P. All right. So the contrapositive and the positive statement, the conditional statement, this one, the positive statement means P implies Q. The contrapositive, not Q implies not P, are equivalent, not equal again. Why not equal? We have one operation here, we have 1, 2, 3 operations. Okay. The inverse is applying the negation for both sides, for both statements. Not P implies not Q. So this is the inverse. Remember, the converse is bringing the implied statement to be at the beginning. So Q implies P. All right. So we have equivalency with contrapositive and the positive statement. P implies Q is equivalent to not Q implies P. Why am I saying this? In proofs, we need these relationships or these explanations, and we will be using them. All right. This is like the proof of P implies Q and not Q implies P. Let's go through it quickly. Now, we are familiar with FF, TT, FT, FT for these two. Also, we are familiar with the negation, TT, FF, TF, TF. All right. The implication. Now, for the implication, you remember it's false if true is implying false. Good. So for this one, only this side, only this field. Why? Because true is implying false here. All right, let's take the contrapositive. All right, the contrapositive, not Q, not this one implies this one. Okay, not Q implies not P. True implies true is fine. False implies true is fine. True implies false is false. The fine means true in this case. I mean, I'm referring to the prominent in this case. True is prominent, only one false. Okay, so let me revise it. Not fine, let me say true. True implies true is true. False implies true is true. True implies false, that's false. False implies false is true. So in that case, we have an equivalency. All right. Let's move a bit. The precedency, which one comes first? If we have a combined statement, which one to be applied first? The highest precedence is given to the negation. So if you find the negation, it should be evaluated first by the computer, not you. By the computer. This is how the computer does it. Then we have and, this is the second, or next, then the single-sided implication or the one-sided implication, then the double-sided implication or the biconditional statement. So if you see something like this, P or Q implies not R. These are statements. This one will be evaluated first, then this one. Then we will take the conditional statement. If you are willing to, if you would like the computer to apply first P or Q, then you should enclose them by parentheses. Parentheses is understood by the computer by put it in the top priority. Do it first. This is how the computer understands it. All right. So in that case, it would be evaluated whatever inside here, then we apply next. If you are interested in implying Q implies not R, then enclose them inside parentheses and they will be considered first with higher priority. But higher priority what? Inside we have a parenthesis. What will be evaluated first? The negation, then the implication. All right. The bitwise operations, instead of having true and false, we can represent true by 1 and false by 0. So let's say we have X and Y, and usually instead of representing here by P and Q, we go on X and Y. A and B is widely available in logic circuits, but also in discrete mathematics. So X and Y here in this case, 0, 0, 1, 1, it's easier, more convenient. If you like it, follow it, there is no problem. 0, 1, 0, 1. Now this is OR and XOR. The outcome, instead of false, it will be 0, 1, 1, 1, 1. Then AND will be 0, 0, 0, 1, only true when they are both true. Okay. XOR, when they are same, the inputs are same, then the outcome is 0. Otherwise, when they are different, the outcome or the output is 1. Alright, this is the end of this part. I'll keep it simple so that we have 2 other parts. Until the next part, have a good time. Goodbye.